Consider this example. I am taking vector space of all polynomials over a field F, and S is some subset of Pn which is defined as F0, F1 and so on. What are these F(i's)? Fn is x raised to power n. So what would be F0? It would be x raised to power 0, that is 1. What would be F1? It will be x raised to power 1, that would be x. F2, it will be x raised to power 2, x square and so on. So these are the elements of S. Alright. Now we have to prove that V is this only. Okay. V is denoted by this Pn only. So we have to prove that vector space is equal to linear span of this S. Now isn't it obvious from the same concepts that we used in proving the theorem? This is quite obvious. We have to prove the second part, that V is contained in you just check at your end. If you are unable to check it, then let me know, I will tell you. Okay. So for the second part, what we now need to prove? We need to prove if I take any alpha from V, then I want to prove that alpha is also in linear span of S. So let me take some alpha from V. Now what type of alphas are there in this V? V is vector space of all polynomials. So how a polynomial look like? Polynomial looks like something like this. This is a random polynomial. Now can I write this polynomial as a0 into 1 plus a1? Can I write like this? And if you can observe, isn't this equal to F0? Isn't it equal to F1? This is equal to F2 and so on. So what we have done, we have written this random function polynomial from this vector space as linear combination of alpha is linear combination of elements of S. So what we say, that linear combination of elements of S, we named this thing as linear span of S. So this is done.